Hi, in this video, we are going to talk about the next topic in our section on polynomials, and that is going to be polynomials with integer coefficients. So we start off with some basic definitions. So let f of x be a polynomial in the set of integer polynomials, and let it be written like this, and f of x is not equal to 0, and f of x belongs to the set z of x. In that case, we'll define something called capacity of f of x. Capacity of f of x is basically the GCD of, excuse me, GCD of all its coefficients, an minus 1 till a1, a0. The GCD of the coefficients of this integer polynomial is referred to as the capacity of this polynomial. And now we can define something called the primitive polynomial. A primitive polynomial is a polynomial of capacity 1. Polynomial with capacity equal to 1. So what does that mean? A polynomial with capacity 1 is a polynomial where the coefficients, the GCD of the coefficients is equal to 1, right? Now, before we go ahead in this chapter, the key idea, the fundamental result that underpins everything here is Gauss's lemma, and we'll state and prove this lemma. It says the product of two primitive polynomials in Z of x, polynomials in Z of x is also a primitive polynomial, So let's try and prove this. Let's try to prove this lemma. We'll do it by contradiction. We will assume that f of x and g of x are two primitive polynomials in Z of x, polynomials in Z of x, and fx times gx, the product, is not a primitive polynomial, So eventually I want to arrive at a contradiction, which will mean that we have proved Gauss's lemma, right? So let's write f of x as an x bar n till a1x plus a naught, and g of x as bn x bar n till b1x plus b naught. So we know that fx times gx is not a primitive polynomial. Therefore, GCD of coefficients of fx times gx is not equal to 1, which implies that there must be a prime p that divides the capacity of fx times gx. When I say capacity of fx times gx, I mean that it is the GCD of the coefficients of fx times gx. So there is a prime p that divides the capacity of fx times dx, which implies that p divides each coefficient of fx times gx. Why? Because the capacity is the GCD of the coefficients, and so obviously GCD divides every coefficient, and P divides the GCD. Therefore, P should divide each coefficient of fx times gx, right? Now we go on to the next screen and we say, because f of x is primitive, we know that P cannot exactly divide all the AIs, right? AIs were the coefficient of f of x. P cannot exactly divide all the AIs, otherwise the GCD would become P. But we know that f of x is primitive, so the GCD of all the coefficients is actually 1, right? So we will say let R be the minimum subscript, the smallest subscript, such that AR, such that P does not divide AR, right? Similarly, we know that G of X is primitive. So we follow the exact same argument. P does not divide all BIs, all BIs. So this implies that there must be S, which is the minimum subscript, such that P does not divide BS, right? The smallest subscript such that P does not divide BS and P does not divide AR, right? Okay. Now let's try to find out the coefficient of x power r plus s in the product fx times g of x, right? So if you think about it, since the polynomials were written, fx was written as a n x bar n and so on till a1 x plus a naught, and gx was written as bn x bar n. Actually, the G polynomial could be degree m, so I should write it as bm x bar m till b1x plus b naught, right? Now think about the product x bar r plus s. How would you get that? We can get it by getting the coefficient of the term AR, which is the coefficient of x bar r, and B bar s, right? BS, which is the coefficient of x bar s from here, right? Plus, you can say AR plus 1 and BS minus 1, plus AR plus 2 and BS minus 2. All of these will give x power r plus s terms, right? So on, till we can say AR minus 1, BS plus 1, right? Plus AR minus 2, BS plus 2, and so on. Think about it. Here we were saying R and we are increasing R and decreasing S, and that sequence of terms. And now we are decreasing R from ARBS and increasing S, and that sequence of coefficients, right? So once you reach the end, you will basically be able to conclude that these are all the ways in which you can get coefficient of x power r plus s, right? Now, what we know is, we know that the sum here, P divides the coefficient of x power r plus s, because we know P divides all the coefficients of fx gx, all coefficients in the product fx gx. We have established that earlier, that P divides all the coefficients. So this sum must be divisible by P. We know that, right? Now, we also know that P divides AI and P divides Bj for I less than equal to r minus 1 and j less than equal to s minus 1. Think about this for a moment. How do we know this? We know that R is the minimum subscript such that P does not divide AR. So any subscript below R, P will divide that coefficient, right? So we are saying P divides AI for any subscript below R. So less than or equal to R minus 1. Similarly, S was the minimum subscript such that P does not divide BS. So any subscript below S, P will divide that coefficient, right? So since we know this, notice that here BS minus 1 will be divisible by P, S minus 2 will be divisible by P. So all of these terms where we are reducing the subscript of B lower than S are all divisible by P. Similarly here, AR minus 1 is divisible by P, this is divisible by P, and all of the subscript, all of the terms here where R is reduced to lower than R minus 1 or lower, these are all terms that are divisible by P. So basically what we are getting is the overall term was divisible by P and all of the terms here are also divisible by p, which follows that AR times BS must be divisible by p. So we can say that since the overall coefficient was divisible by p and so many other partial terms here are divisible by p, it follows that p should divide ARBS, but that is a clear contradiction, because that means that p divides AR or p divides BS, but we have already selected AR and BS as such that p cannot divide that, right? So we have arrived at a contradiction, and basically that means fx times gx is also a primitive polynomial, right? So this is the proof of Gauss's lemma, and now we'll be using Gauss's lemma freely through the rest of the discussion here, right? Let's look at the second point that I wanted to talk about. Let fx belongs to q of x and fx is not equal to 0, then there exists a rational number a not equal to 0 such that a times f of x is a primitive polynomial in z of x, is a primitive polynomial in z of x. So what this is saying is, if you take any polynomial in the set q of x, which is the set of polynomials with rational coefficients, then we can find a rational number a such that the product of a and f of x is a primitive polynomial in z of x. In addition, what we can also say that if there exists okay, there was a slight interruption. We'll continue with this. The statement that I was saying was this: let f of x belong to q of x. F of x is a rational polynomial. There exists a rational number a not equal to 0 such that a times f of x is a primitive polynomial in z of x. Primitive polynomial in z of x. So what does this mean? That any rational polynomial you can take and you can find a rational number, so that when you multiply it with that rational polynomial, you will end up getting a primitive polynomial in z of x, right? So if there exists a rational number b such that b times f of x is also a primitive polynomial, apart from a, if you can find another rational number b such that b times f of x is also a primitive polynomial, then a must be equal to plus or minus b. So basically this means that for every rational polynomial, every non-zero polynomial in q of x, there corresponds a primitive polynomial in z of x. Primitive polynomial in z of x. So we are stating this idea without proof right now, but you just need to use the property that for every rational polynomial in q of x, there is a non-zero primitive polynomial in z of x, right? So this property basically means that if you want to talk about if a function f of x is reducible is reducible in Z of X, we only need to consider the case that we only need to think about whether f of x is a primitive polynomial in Z of X. To consider the case that f of x is a primitive polynomial in Z of X. So we'll explore these connections later. So let's get into it in detail soon. So let's look at the third property. Let f of x be a polynomial belonging to the set Z of X and f of x be a primitive polynomial. So what is a primitive polynomial? It is a polynomial with capacity 1 where all the coefficients have GCD 1. If f of x is reducible in Q of x. What do I mean by reducible? It means that it can be split apart and decomposed as a product of two polynomials in Q of x. It implies also that f of x is reducible in Z of x. So if f of x was a primitive polynomial and f of x had factors in Q of x, that means f of x will have factors in Z of x. Okay. So how do we think about this? So we say let f of x be equal to g of x times h of x, where g of x and h of x belong to Q of x. This is what it means when we say f of x is reducible in Q of x, right? Now here, obviously, we can say that g of x and h of x are the factors of f of x in Q of x, right? And g of x and h of x itself belong to the Q of x polynomial, a Q of x set of polynomials. So we know there is a rational number a such that a times g of x is a primitive polynomial, right? It's a primitive polynomial. And similarly, there will be a rational number b such that b times h of x is also a primitive polynomial, right? So basically, what we can say is that ab times f of x, which is equal to a times g of x into b times h of x, is a product of two primitive polynomials, right? Because we know that a times g of x is a primitive polynomial. This is from the previous point that for every rational polynomial, there is a primitive polynomial in Z of x, right? So since g of x was a rational polynomial, we have a times g of x is a primitive polynomial in integers, right? And similarly, b times h of x is a primitive polynomial in Z of x again. So if you think about ab times f of x, that can be written as a times g of x multiplied by b times h of x. And these are the products of two primitive polynomials. So basically what I'm saying is ab times f of x is equal to a times g of x multiplied by b times h of x. And these themselves are primitive polynomials in Z of x. Both of them. So by Gauss's lemma, the product of two primitive polynomials, primitive polynomials is itself a primitive polynomial. So what we conclude from here is ab times f of x is a primitive polynomial, right? So basically what we can say that means that our f of x is also a primitive polynomial, and AB must be equal to plus or minus 1. AB must be equal to plus or minus 1. So you can say that the choice of B must be 1 by A or something like that, right? If A was a rational number that made G of X into a primitive, we can choose 1 by A for H, right? The idea, basic idea is simple. It is saying that once you have a function that is reducible in in the set of rational polynomials, once you have a rational polynomial which is reducible, then we also have the fact that that polynomial is also reducible in the integers polynomial set, right? We are using the Gauss's lemma and the previous property in order to prove this. The next idea is the criteria for irreducibility given by Eisenstein. Eisenstein's criteria for irreducibility. So we will not do the proof of this criteria. However, I'll just state the criteria and help you use it in problems. So let f of x be equal to an x bar n, so on till a naught, be a polynomial with integer coefficients, with integer coefficients, and n is greater than equal to 1. The degree of the polynomial is greater than equal to 1. Now, if there is a prime number p, if there is a prime p such that p does not divide an, p divides ai for I goes from 0, 1 till n minus 1, and p squared does not divide a naught, then we can say that f of x is irreducible in z of x, which also implies that f of x is irreducible in q of x. Irreducible in q of x. So basically, what are we saying here? We have a polynomial with integer coefficients and degree greater than or equal to 1. If there is a prime p such that p doesn't divide the highest coefficient, p doesn't divide an, but p divides all the other coefficients. Every other coefficient is divisible by p, and p square does not divide the last coefficient, the constant term. In that case, f of x is irreducible in z of x, and also that implies that f of x is irreducible in q of x, right? In particular, applying Eisenstein, we can say that any polynomial of the form x power n plus 2 is irreducible. Why? Because we can say that our prime p is 2, and p does not divide an 1. The first term is 1. However, p divides 2, which is the other coefficient, but p square does not divide 2, right? So this polynomial follows the criteria of Eisenstein's criteria. Therefore, this polynomial is always irreducible in z of x or q of x, right? So now that means that in the set z of x or q of x, we can find irreducible polynomials of any degree. Irreducible polynomials of any degree. Why? Because x power n plus 2 is always irreducible in this set, right? And this n is variable, so it can have any degree. Remember that in the set of R of x, irreducible polynomials can only have degree 1 or degree 2, Whereas in the set of C of x, irreducible polynomials can only have degree 1. So this is a special property of Z and Q sets. Using Eisenstein, we can find irreducible polynomials of any degree. Also remember that the Eisenstein criteria is only a necessary condition, it's not a sufficient condition. If Eisenstein criteria is true, the polynomial is irreducible. However, there are many polynomials. No, I made a mistake here. Eisenstein's criteria is a sufficient condition. If it is true, the polynomial is irreducible. However, it is not necessary. There are many polynomials that you can find which will not satisfy Eisenstein's criteria but are still irreducible in Z of x. So it's a sufficient condition. If Eisenstein is valid, polynomial is irreducible, but the converse is not true. If the polynomial is irreducible, it may still not satisfy Eisenstein's criteria. So you need to remember that. Okay. The next result that I want to talk about is this. Let P be a prime. This is a consequence of Eisenstein. Let P be a prime. Then define phi of Px as x power p minus 1 plus x power p minus 2 and so on till x plus 1. This phi of px is irreducible in q of x. Is irreducible in q of x. How? We can show that f of x, let's take f of x as phi of px plus 1. And that will become basically by the geometric series formula, it will become this. This is GP formula that I'm applying to this. So this is becoming x power p minus 1 plus pc1 x power p minus 2 and so on till pcp minus 1. This is the polynomial that comes, which is phi of x plus 1. And now you can check yourself that this polynomial satisfies Eisenstein's criteria. Eisenstein's criteria. We can take the prime number PCP minus 1 is P, right? So we can take the prime number P itself. P does not divide 1. P divides each of PC1, PC2 and so on till PCP minus 1. But P squared does not divide PCP minus 1. So it satisfies the criteria and therefore it is irreducible, right? Okay. There are a couple more interesting properties which we will discuss and state without proof. However, it is highly unlikely that you will encounter them in problems. So I will just state it. Let f of x be a polynomial with integer coefficients. With integer coefficients. The leading coefficient is 1. The leading coefficient is 1. And f of 0 is not equal to 0. F of 0 is not equal to 0. If f of x has only one single root alpha, such that mod of alpha is greater than equal to 1, then f of x is irreducible in z of x. Now, you will not encounter this too many times, but in case, I'm just letting you know, this is a nice criteria. Another one is like this. Let f of x be a polynomial with integer coefficients of degree n, n is greater than equal to 1, and let alpha 1, alpha 2 till alpha n be all its complex roots. all its complex roots. If there is an integer k, if there is an integer k such that k is greater than 1 plus real part of alpha j, where j can vary from 1 to n, and mod of f of k is a prime, then f of x is irreducible. F of x is irreducible in the set z of x. Again, slightly complicated criteria here. F of x is a polynomial with integer coefficients. Alpha 1 to alpha n are all its complex roots. If there is an integer k such that k is larger than 1 plus the real part of each root, k should be greater than 1 plus the real part of each root, and mod of f of k should be a prime, then f of x is irreducible. So we will look at some problems, mostly the questions on irreducibility. You will do it by using Gauss's lemma and possibly Eisenstein. These are highly specialized cases that you may or may not encounter. Let's look at a few problems to underline what we have learned so far. Example 1 is this. Determine whether the polynomials x power 4 plus 1 and x power 4 plus 4 are reducible in z of x. Okay, so we can think of this x power 4 plus 1. If it is reducible, you will want to have possibly quadratic factors for it, right? You could possibly make quadratic factors like this, x square plus cx plus d. So if you make quadratic factors here, you can multiply it out. You can multiply it out and get equations like this. A plus c is 0, b plus d plus ac is 0, ad plus bc is 0, and bd is 1. So we are assuming that it is reducible and we are getting quadratic factors in this way. And in case you are getting quadratic factors, you are getting these equations once you compare coefficients. And what you will see here is that when you solve this, you will get a square is equal to -2, which is not possible, not possible. So that is one way to deduce that it is impossible to factorize this in this way, right? So here we are using the method of undetermined coefficients. We are assuming unknown coefficients and finding equations on them and trying to solve it here, right? On the other case, for x power 4 plus 4, there is a direct factorization available. You can factorize it immediately like this. This is a standard factorization, so it is clearly reducible. And the first one was irreducible because it is impossible to write it as a product of two factors. The second one is directly factorizable. Let's look at another example. Here we have to check the reducibility of the polynomial x power 5 minus 3x power 4 plus 9x cube minus 6x square plus 9x minus 6. We have to check whether it is irreducible in z of x. So this question has been set up in order to check whether you know Eisenstein. So you can use the prime number p is equal to 3 here. We can say that 3 does not divide 1, which is the an term, the highest power. 3 divides ai, where I goes from 0 to n minus 1, because it divides all of these terms, -3, 9, -6, 9, and -6. However, 3 square does not divide a0, which was 6, -6. 3 square is 9, 9 does not divide -6 exactly. Therefore, This polynomial satisfies all the criteria of Eisenstein's condition, and we get that this is a irreducible polynomial by Eisenstein. Let's look at slightly more involved questions now. This is example 3. Let a1, a2 till an be integers that are different from each other, that are different from each other. Prove that x minus a1, x minus a2, product till x minus an minus 1 is irreducible in z of x. Okay, so what we will do here is we have to prove that this is irreducible. We'll try to do a proof by contradiction. So this is the standard approach that you should take in problems like this. So what we will say is, let's assume fx is equal to the product of gx and hx, right? And gx and hx are non-trivial decomposition of f of x. Then therefore we know f of ai is equal to -1, right? If you put any of the ai's here, obviously I goes from 1 to n. If you put any of the ai's, notice that this part will vanish. So f of ai will become -1. Here, what is our f of x? F of x is, we are calling f of x as this thing, x minus a1, x minus a2, x minus an minus 1. That is my f of x. And we know that f of ai is -1. So that means that g of ai times h of ai is equal to -1, which means that one of g of ai is equal to 1 and the other is -1. So without loss of generality, we can assume either one to be 1 and the other one is -1. So that therefore means that g of ai plus h of ai is equal to 0. We know this now. And this relation is true for all ai's where I goes from 1 to n, right? This relation is true for all the ai's for I goes from 1 to n. What have we done so far? We have assumed that f of x is reducible. We have written it as a product of gx and hx. And because f of ai is -1 for all the ai's, we know that g of ai has to be +1 and h of ai has to be -1 or vice versa. So this is true for all the i's from 1 to n, right? Therefore, we can say the polynomial g of x plus h of x has at least n different zeros, because the zeros are a1, a2 till an. We know that g of ai plus h of ai will add up to 0. It has n different zeros, but we know fx was equal to the product of gx and hx, and that implies that the degrees of gx and hx are less than n. Because fx has degree n, the degrees of gx and hx are less than n. So how can it have n different roots? That means, therefore, gx plus hx, since it has more roots than its degree, gx plus hx is identically equal to 0. So therefore, we get gx is equal to minus of hx. And now we are getting f of x as negative of hx whole square, right? Since gx can be written as minus of hx, our f of x is becoming negative of hx whole square. But now this leads to a contradiction, because we know that the f of x function was like this, x minus an minus 1, the leading coefficient of f of x is +1, whereas the leading coefficient here is negative. Leading coefficient of negative of hx whole square is negative, right? So we have gotten a contradiction based on the fact that the leading coefficient will have opposite signs, and that means that f of x cannot be written as gx times h of x, which was our initial assumption. So basically that proves that f of x is irreducible. Let's look at one last question. This says let f of x be an integer polynomial of degree n, prove if there exists at least 2n plus 1 distinct integers m such that mod of f of m is a prime, then f of x is irreducible in z of x. Okay, so we have an integer polynomial of degree n, and we have to say that if there exists at least n 2n plus 1 or more distinct integers m such that mod of f of m is a prime, then f of x is irreducible. Again, we'll try a proof by contradiction. We'll say let f of x be decomposed in terms of g of x and h of x. The degree of f is n, and let's say the r is degree of g and s is degree of h. So we know that n is equal to r plus s because this is the product, right? Now we know that since g of x is not a constant polynomial, because that would make this decomposition a trivial decomposition. If g of x is constant, then h of x is simply a multiple of f of x. We are not talking about such decompositions here, right? So since g of x is not a constant, we know both g of x plus 1 and g of x minus 1 have degree r. So at most r roots, right? So at most r integers m, those integers are called m, let's say, that make g of m equal to 1, and similarly at most r integers m, r roots m dash, which make g of m dash equal to -1, right? What are we saying? We are saying g of x is a polynomial of degree r. So g of x plus 1, g of x minus 1, both are polynomials of degree r. So if you think of the equation g of x plus 1 equal to 0 and g of x minus 1 equal to 0, the maximum number of roots of this equation is r, and this equation is also r. So there are integers at max such that g of x is plus 1 and r integers such that g of x is -1. That is the maximum case. So what we can conclude from here is there is at most 2r integers which make g of x equal to ±1, right? With the exact same argument, we can say that there are at most 2s integers which make h of x equal to ±1, right? Now think about the condition that we have. If an integer m, if an integer m makes mod of f of m, which is actually equal to mod of g of m times h of m, to be a prime, to be a prime, how can this be a prime if it is a product of two integers, right? It can't be unless one of them is plus or minus 1, right? So then we can say then g of m is plus or minus 1 or h of m is plus or minus 1, right? The only way this can happen is if either g of m is plus or minus 1 or h of m is plus or minus 1. So here the maximum number of cases is less than equal to 2r, and here the number of cases is less than equal to 2s, right? We have just now seen that. So therefore, the total number of ways in which this can be a prime is less than equal to 2r plus 2s in the absolute maximum number of cases, right? So that is equal to 2n, right? So the number of ways in which integer m can be taken such that mod f of m is a prime is less than equal to 2n. But that is contradicting our hypothesis. The hypothesis says that there are greater than equal to 2n plus 1 integers such that mod of f of m is a prime, right? And we have proved here that it must be less than equal to 2n. So that means we have got a contradiction, and that means we cannot write f of x as g of x times h of x, and therefore f of x must be irreducible, right? So basically, in this section of the course, we have looked at primitive polynomials, we looked at Gauss's lemma, and then we started looking at criteria for polynomials to be irreducible if they are in the set Z of x. Eisenstein is the simplest criteria, and many times the proof methods are done by a proof by contradiction. We have seen some examples of that as well. So that concludes the theory for this section, and I'll see you next time for the video on interpolation of polynomials and differences of polynomials. So I'll see you next time.